Hi everybody, welcome back to What's Up Physics. My name is Mariah, and today we're going to be learning about elevators. You're going to see with elevator problems that the motion of the elevator affects the net force on the object inside the elevator. This is because depending on the direction of an elevator's acceleration, the normal force of the object can either increase or decrease. You might be confused on how the normal force can change. After all, it's always supposed to be equal to the gravitational force, right? No. While stationary, the normal force represents how much a surface must push up on an object to keep it from accelerating into the surface. In this scenario here on the left, the normal force must counteract the gravitational force, which pulls the box down. So the ground pushes back up with the normal force equal to the Earth's pull or the gravitational force. But over here on the right, the box is already being pulled up a little because of this tension force. So the ground doesn't need to push as hard to keep the box out of the ground, and the normal force is less. As you can see, the normal force can change depending on the scenario, and this is something you'll need to understand when working with elevators. Most elevator problems will deal with the person standing on a scale. Your scale reading tells you how much you weigh, but it doesn't actually measure the gravitational force or weight. It's actually measuring the normal force. When you're standing still on a scale, the normal force and gravitational force acting on you are equal, so your scale reading gives you your true weight. However, accelerating vertically can change the normal force, and since that's what the scale is measuring, it now gives you your apparent weight. Side note, in the everyday world, scales read in pounds or kilograms. Pounds are a measure of weight, just like newtons, which can also be used as units for a scale, and both are acceptable units for force. But kilograms are a measure of mass, or how much stuff you're made of. So when you see a scale displaying kilograms, it's actually reading that normal force, or true weight, and then converting that into units of mass. Now we're going to do some practice problems together. Example number 1. You, with a mass of 72 kilograms, stand on a scale in an elevator. While it descends at a constant velocity of -5 meters per second, for part A, we're asked to find what the net force acting on you is. Well, according to Newton's second law, the net force is equal to the mass times the acceleration. And since we're at a constant velocity, our acceleration is 0 meters per second squared. And that makes the net force equal to 0 newtons. For part B, we're asked to find the gravitational force that's acting on you, and we have our equation that the gravitational force is equal to mass times the acceleration of gravity. Your mass is 72 kilograms, and unless you're a character in Charlie and the Great Glass Elevator, your elevator is probably on Earth, where the acceleration of gravity is -10 meters per second squared. So the gravitational force acting on you is -720 newtons. And for part C, we are asked to find what the normal force acting on you is equal to. Well, since there's no net force, the upward and downward forces acting on you must be equal in magnitude. So the normal force is equal to the gravitational force, but since it acts in the positive direction, we'll write positive 720 newtons. Example number 2. Now the elevator is coming to a stop at your floor, and you're going down. You, with a mass of 72 kilograms, find that it takes 2 seconds to go from a velocity of -5 meters per second to rest. For part A, we're asked whether the scale will read more, less, or the same value as your true weight, and they want us to explain as well. So, you're going down and coming to a stop, which means that you're slowing down. And when you're slowing down, acceleration points opposite the direction that you're going. So you are accelerating in the upward direction. Acceleration and the net force point in the same direction, and for the net force to point up, the upward forces acting on you must be greater than the downward forces. So in this scenario, that means that the normal force is greater than the gravitational force acting on you. And the scale reads the normal force, which is greater than your true weight, or the gravitational force. For part B, they're asking us what the what the net force is, and whether it should be positive or negative. Now, to find the net force, we need to know the mass and the acceleration per Newton's second law. We're given your mass, but to find your acceleration, we're going to have to use kinematics equation number 1, which states that the final velocity is equal to the initial plus the time times the acceleration. So now you can just plug in your values of 0 for the final velocity, -5 for the initial, 2 for the time, and you can isolate for the acceleration, which you get is 2.5 meters per second squared. And then you can plug this into Newton's second law along with the mass of 72 kilograms, and you'll get that the net force is equal to 180 newtons. And we get a positive number, and that matches up with what we were just saying earlier, that acceleration is positive because you're slowing down while going down, and since acceleration and the net force must have the same sign, the net force has to be positive. And for part C, they're asking us what the gravitational force acting on you is. Well, the gravitational force is always equal to your mass times the acceleration of gravity. And since you haven't dropped mass or moved to a different planet since the last example, the gravitational force is still negative 720 newtons. Don't know if you can read that. And for part D, they want to know what the normal force acting on you is. To find the normal force, we can just set up our equation for the net force and then isolate the normal force. So the net force is equal to the up forces, or the normal force, minus the down forces, or the gravitational force. And now I'm just going to plug in the net force and the magnitude of the gravitational force. And then I'll isolate for the normal force, which is 900 newtons. And just like we said, that's bigger than the magnitude of the gravitational force, which is only 720 newtons. Example number 3. You, still with a mass of 72 kilograms, are now going up in the elevator, and when you get to your floor, the elevator comes to a stop. You find that it takes 4 seconds to go from a velocity of 5 meters per second to a stop. Part A asks us whether the scale will read more, less, or the same value as your true weight, and to explain. Now you are going up and you're stopping, which means that you're slowing down. And when you slow down, your acceleration points behind you, so it's going to point downwards. The net force points the same way as your acceleration, so the net downward forces acting on you are going to be greater than the upward forces, which means that the normal force is less than the gravitational force. And since a scale measures your normal force, it's going to give a reading that is less than your true weight or your gravitational force. Part B asks us to find the net force acting on you and whether it's positive or negative. To find the net force, we'll again use Newton's second law. But first we need to find our acceleration, and we'll do this with kinematics equation number 1, which states that the initial velocity is equal to, the final velocity is equal to the initial plus the acceleration times the time. And we can plug in our values here, and then isolate for the acceleration, which is negative 1.25 meters per second squared. And now that we have that, we can plug that into the second law, which states that the net force is equal to the mass, 72 kilograms, times the acceleration. And that gives us that the net force is equal to negative 90 newtons. And as we already discussed, the net force would be negative because you're slowing down while going up, which means that the acceleration is negative. And the net force and the acceleration point in the same direction, so the net force would also have to be negative. So our math matches up with this. Part C asks us what the gravitational force acting on you is. Like we already said, the gravitational force stays constant unless your mass or the acceleration of gravity change. And since presumably neither of these things happen, the gravitational force is still negative 720 newtons. Part D asks us what the normal force acting on you is. To find the normal force, we can set up the equation for the net force and isolate for the normal force. So the net force is equal to the up forces, or the normal force, minus the down forces, the gravitational force. Now you can plug in the net force of negative 90 and the magnitude of the gravitational force, which is 720. And then you isolate for the normal force, and you get that it's positive 630 newtons. And just as we predicted, it is less than your true weight, which has a magnitude of 720 newtons. Example number 1. The figures below depict situations where a person is standing on a scale in 8 identical elevators. Each person weighs 600 newtons when the elevators are stationary. Each elevator now moves or accelerates according to the specified arrow that is drawn next to it. In all cases where the elevator is moving, it is moving downward. Rank the figures from greatest to least on the basis of the scale weight of each person as is registered on each scale. And you can use that the acceleration of gravity is equal to 10 meters per second squared. Right, so the scale reading gives us the normal force acting on each person. So we're looking to see who has the biggest and smallest normal forces. Now, the greater that the normal force is, the greater the net force is in the upward direction. And per Newton's second law, the net force is equal to the mass times the acceleration. But in this scenario, each person is of the same mass, right? Because when you divide their true weight, which is the same for every person, by the acceleration of gravity, you get their mass, and that's equal to 60 kilograms. So, if they all have the same mass, then that tells you that the net force is actually proportional to the acceleration. So the people with the greatest positive acceleration will have the greatest normal forces acting on them, and the people with the greatest negative acceleration will have the smallest normal forces acting on them. So all we really need to do is to rank the accelerations. But hang on, do we need to take the velocities of the people into account? Actually, no. Velocity doesn't affect force in any way, so we can disregard that. In fact, nothing about the motion of the people, not the velocity, not the direction they're going, matters to force outside of acceleration. So, our answer will be A equals B, E, and they're both greater than C, which equals D, which equals F, and that's greater than B, which is greater than G, which equals H. Example number 2. An elevator is holding a person of mass 50 kilograms, and it's moving downward while slowing down. How does the magnitude of the force the elevator floor exerts on the person, which we'll call F, compare to the magnitude of the gravitational force, which is mg? Well, as we discussed in the last problem, speed and velocity have nothing to do with force, so we can automatically rule out option D. Now, if you're moving down and slowing down, your acceleration points behind you, which is in the upward direction. And this means that the up forces are greater than the down forces because your net force also has got a point in the upward direction. And this means that the normal force, or the force the elevator floor applies to the person, is greater than the gravitational force. So our answer is B. Example number 3. A box of mass m sits atop a box of mass 3m inside an elevator, which is moving upward and speeding up. F sub m is the magnitude of the force exerted on the box of mass 3m by the box of mass m, and F sub 3m is the magnitude of the force exerted on the box of mass m by the box of mass 3m. F sub g is the magnitude of the gravitational force on the box of mass m. F sub n is the force the elevator exerts on the box of mass 3m, the elevator floor specifically. Which of the following correctly ranks the forces? So since the system is moving upwards and speeding up, both acceleration and thus the net force must point upward. All the components in the system have to have the same acceleration, and so all their net forces have to point upwards. To solve this problem, we'll draw FBDs of both the boxes. Let's start with the box of mass m. Like the problem says, it has a gravitational force acting on it, which we'll label as F sub g. It also has a normal force acting on it, which is the force the box of mass 3m applies to it. These are the only forces acting on this box, and for the net force acting on it to point up, F sub 3m must be greater than F sub g. Now let's do the box of mass 3m. It has a gravitational force acting on it that is 3 times greater than the one acting on this box, because its mass is 3 times greater. It also has another downward force acting on it, which is the force that this box applies to it, F sub m. And the magnitude of F sub m is the same as the magnitude of F sub 3m, because Newton's third law states that two objects in contact exert equal but opposite forces on each other. So that looks like this. Now, in order for the net force on this box to point up, there has to be an upward force acting on the box that is larger than the sum of these two forces. So we'll draw a super big normal force and label it F sub n, like the problem says. Now that we've done this, it's pretty easy to see how we should rank the forces. F sub g is the smallest, F sub m and F sub 3m are equal in magnitude, and F sub n is the largest. So our answer will be choice A. Example number 4. At Disneyland, the Guardians of the Galaxy breakout ride takes riders straight up in a tower in an apparatus with seats and then releases them, letting them free fall back to Earth before stopping them safely above the ground. Which of the following indicates the magnitude, F, of the gravitational force exerted on a rider of mass m on the way up and on the way down? The gravitational force near the surface of a planet is always equal to the mass of the object the force is being applied to times the planet's acceleration of gravity. Since the ride doesn't cause you to grow a limb or take you to Mars, your mass and the acceleration of gravity stay the same. And so no matter which way you're going, the gravitational force is equal to mg. So D is the correct answer. Example number 5. A person stands inside an elevator. The total mass of the person elevator system is 2,000 kilograms. If the elevator is just starting to go up and is speeding up with an acceleration of 6 meters per second squared, what is the tension in the cable holding the elevator? So when you're speeding up, acceleration points in your motion of direction, which in this case is up. And this means that the net force also points up. The only forces acting on the system are the tension and gravitational forces, and so the upward force, or the tension force, must be greater than the downward force, or the gravitational force. We can set this up as an equation. The net force is equal to the up forces, or tension, minus the down forces, or gravity. And we know that the net force is equal to mass times the acceleration, thanks to Newton's second law. So that's 2,000 kilograms times 6 meters per second squared, which gives us 12,000 newtons. And we know that the gravitational force is equal to mass times the acceleration of gravity. So in this case, 2,000 kilograms times negative 10 meters per second squared, and that's negative 2,000 newtons. Now we can plug the net force and the magnitude of weight into this equation. So that's 12,000 is equal to the tension force minus 20,000 newtons. And then you isolate for the tension force and you get that it's equal to 32,000 newtons. Example number 5, part B. If the elevator is going up and slowing down with an acceleration of negative 6 meters per second squared, what is the tension in the cable holding the elevator? When you're slowing down, acceleration points opposite your direction of motion, or in this case, down. And since acceleration and the net force point in the same direction, this means that the downward forces acting on the system are greater than the upward forces. Now, the only forces acting on the system are the tension force from the cable and the gravitational force. So, the gravitational force is greater than the tension force. Just like last time, we'll set up an equation with all the forces and the net force. The net force is equal to the upward forces, or F sub t, minus the downward forces, or F sub g. And we know that the net force is equal to the mass times the acceleration, thanks to Newton's second law. And we'll just plug in our values of 2,000 kilograms for the mass and negative 6 meters per second squared for the acceleration to get that the net force is equal to negative 12,000 newtons. And neither our mass nor the acceleration of gravity have changed since part A, so the gravitational force is still equal to negative 20,000 newtons. Now we can just plug in the net force and the magnitude of weight into the equation. Let me use a different color to make it easier to see. So negative 12,000 is equal to the tension force minus 20,000. And then you just isolate for the tension force, and you get that it's equal to 8,000 newtons.
Our next lesson will be on centripetal acceleration and the centripetal force. If you like this video, please be sure to like, share, and subscribe. Bye for now.